Welcome to a lesson with Dr. Powell. Let's take a look at projection and a plane. Notice how we have this path represented by this arrow right here. That's like going in the X direction. And this one up here is like going in the Y direction. And then let me just kind of go like this for a second. Let's take a look at how we can kind of visualize this. So there's a slope right there. Okay, so you have a change of X, and then this is the projection in the direction of Y, or Z, the direction of Z. So this is like change of Z, given kind of going along this arrow path right here. Okay, now let's take a look again and go like this and see. So there's in Z now, we also have the change of Z right here by the change of Y. And if you look at this for a minute, we have right here, we have a line that goes from here to here and an arrow that goes from here to here. Oh, sorry, let's and from here to here. Okay, so you see the sum of these two arrows on the plane itself. So, or these two vectors. If you were to add those two vectors, you'd actually get this vector that's on the plane. So this vector plus that vector is equal to that vector. And notice that if we take the projection of this one and plus the projection of this one, so the projection of this one onto the vertical and the projection of this one onto the vertical, and add those two together, we end up getting the projection overall from here to here onto the vertical. So if we were to, so right here, so if we were to take this and go right to here, right? Kind of the projection onto the vertical there. See, this one plus that one equals that projection. We can visualize that here by just kind of rotating this around and kind of see how those two guys just add together. And now in the input, this is what's happening in the input. We have this is how the inputs change. The input starts here, and then it goes to this place right here. Now notice how that input is made up of two parts, this part and this part. This, you could say like that's the change of X, that's the change of Y. And overall, the ultimate rise that we get for given this run, suppose this is the run, okay, made up of a movement here and here, but you can ultimately just think of the run as being this vector, just the sum of those two. So this is the run. Now for that particular run, we can rotate this a little bit. Okay, and let's kind of look at this for a minute. So for that particular run, we can visualize the run right here. Okay, for that particular run, we have a rise, right? So, and that rise is just the projection of this line right, this straight line right here onto that vertical right there. And we can represent that that as a dot product, because if we take the projection of this part of the line onto the vertical and that part of the line onto the vertical, let's see. So this would be, as we take that that projection and that projection. Now, how do we get this projection? What we do is we think of slope, and the slope of this line, if we take that slope So slope in the x direction, we'll call the slope in the x direction of, and suppose that this plane of the surface is f. So the slope in that direction, let's just call fx. And then if we multiply that slope by run, you're actually going to get rise in that direction. Then if we add to that the slope, let's see, this right here. Now, what is this? This is going to be the slope in the y direction times the run, and that gives you the rise in z. So this is the change of z on this part. This is the change of z on this part due to x, due to y. And that's basically because if you think of this as being slope in just the x direction, and if you think of change of z over change of x, if you were to multiply both sides by change of x, you just get fx change of x, and that's equal to change of z. So hence we get the rise in that direction is right here, and the rise in the other direction right here. This is like a dot product. Indeed, it's a dot product. If we were to think of this as being like fx, fy, slope in the x direction, slope in the y direction, and normally we represent dot products, especially when we're going to put lots of different dot products together. It's because we're going to be thinking of lots of different projections pieced together. We like to think about matrix multiplication. It's a nice way of putting and organizing different types of dot products. So if we're doing lots of different projections, which we will be when we think about a derivative idea, we like to think of lots of different dot products. In this case, we have this and change x, change y. So we have two vectors, but we've written them as matrices with a space, not a comma here, just a space. And this one is as a row, this one's as a column, but this just means take the dot product. Fx times change of x plus fy times change of y. And the result of doing this is, so this is run, and this is like the function that takes run to rise. So this is kind of a little description about that idea. Again, this type of notation can be used and organized in multiple formats, especially when we have more inputs and outputs than we do just here. But hopefully that gives you a little bit of an idea. Thank you for watching.